Mara completed her PhD at the University of York, United Kingdom, followed by a postdoc at the University of Edinburgh, United Kingdom, and a research software engineer position at her alma mater. She's currently a lecturer at the University of Manchester, United Kingdom, working on advanced models of magnetism for energy-efficient devices. And today she will present her work titled Ultrafast Spin and Spin Lattice Dynamics in Advanced Magnetic Materials. Mara, your talk is 25 minutes long, followed by 5 minutes of questions and answers. In the top center of your screen, next to the option to stop sharing, you should eventually see a timer showing the remaining time. Also, to ask questions, everyone, please write them down in the chat or raise your hand. So please, Mara, begin your presentation whenever you are ready. Thank you very much.
Okay, hello everyone, and thanks Ricardo for the very nice introduction. I'm very happy to be here at the conference, especially since back in 2020, I helped out a bit organizing the first around the clock, around the globe conference. So it's a big honor for me to return here after 5 years as a speaker. I'd like to thank all the committee for organizing such a wonderful event this year and for contributing to this event in the past 5 years. So this is a talk about modeling of spin and spin lattice dynamics in magnetic materials. So I will I hope you see the slides well.
Yeah, we can see them.
Okay. So I'll talk about the theoretical framework behind atomistic spin and spin lattice dynamics and how we've implemented this into the open source code Vampire. And then I'll spend some time discussing two applications in the area of two-dimensional magnetic system and magnon-phonon coupling. So with the current development of AI models and also online content, the global data sphere has increased significantly up to currently reaching 175 zettabytes. So we need to think of ways to efficiently store information and develop recording media technologies which are more energy efficient. I'm having a bit of problem switching between slides. Okay. Magnetic storage still remains the backbone of recording technologies. Since it's cheap, scalable, we need more storage, we can just add more hard disk drives and non-volatile. However, the development of this technology relies on fundamental aspects which are called this trilemma, which governs the connections between fundamental aspects such as signal-to-noise ratio, thermostability, and writability. So to push recording media technologies, we need to take into account all of these limitations. So over the years, we have moved from longitudinal to perpendicular recording, and now we are in the area of heat-assisted magnetic recording, where we use materials with a very large anisotropy, as iron platinum, and a laser pulse to heat up the system and allow writing the information at accessible fields. And currently, this technology exists in the form of the Mosaic hard disk drive developed by Seagate. However, it took about 20 years to reach from the concept of heat-assisted magnetic recording to the device level. So we need to start to think about now what will be the next technology that will help shape our storage devices. So for this, we can investigate various switching mechanisms and how these can be used for next generation hard disk drives. So currently we use a magnetic field to write our information in iron platinum bits. However, there is a possibility to switch the magnetization and write the information in the absence of a magnetic field, and this has been achieved for a category of materials called ferrimagnets in this iron gadolinium compounds. It doesn't rely on magnetic fields, so it can be more energy efficient. And also it has been proposed this mechanism of switching the magnetization or controlling magnetization by coupling your laser pulse excitation to the phonons, to the lattice vibration, which will modify the local properties of your magnetic system and hence the anisotropy, and can drive precession and hopefully switching. And this type of phenomena is assumed to employ less energy. So it's a more energy-friendly way to write your information. Current recording media technology use nanometer scale systems, nanometer scale grains. And to model such system, we employ atomistic spin dynamics. And to bring a bit of context, historical context into the atomistic spin dynamics, I'm just quickly recalling the models that shaped our understanding of interacting spins. So we start with the Ising model, which was developed in the 1925, around 1925, and assumes interaction between spins pointing only in two directions, spin up or spin down, and these are coupled by exchange energy. And then Heisenberg came later and allowed the spin to evolve around the sphere. So this is currently what we employ in our atomistic spin dynamic simulation. Our spin is free to evolve around a unit sphere. And then I also thought to mention here the Hopfield model, which basically connects the spin to the all neighbors. This has been more employed in neural networks. However, the fundamentals are drawn from magnetism and has recently received in 2024 a Nobel Prize. So to describe a bit in more depth atomistic spin dynamics, what we do, we assign to each atom in our magnetic material a spin, which is a classical entity, and we allow this to evolve according to the Landau-Lifshitz-Gilbert equation. So we'll have this precession and this damping term. So we numerically integrate the Landau-Lifshitz-Gilbert equation. In this equation here, we have this effective field, which can be calculated based on the Hamiltonian of our system and can be augmented by a thermal field. So we can now perform finite temperature simulation by connecting it to a thermal field and Langevin dynamics. We can have various, depending on the material properties, the Hamiltonian can be extended to include multiple contribution. In the simplest case, we have the exchange, and the exchange matrix can be developed in such a way to include the antisymmetric terms, also called the Janoshinsky-Moriarty interaction terms, which give rise to skyrmions. We can have high-order exchange interactions, as shown here by the biquadratic exchange, and many others energy terms. And one aspect we've been looking to in the past year is the interaction of magnetic system with laser pulse excitations and how we can use that for technological applications. So in this framework, the laser connects to the free electrons in our magnetic systems. There's an increase in the electronic temperature, which further thermalize with the lattice and the spins. What we do in atomistic spin dynamics, we basically model what's called the two-temperature model, as shown in this coupled equation here, that gives the profile of the evolution of the electronic and phonon temperature as function of time. And then we couple our spins to the electronic path via atomistic spin dynamics, and we are able to look into the evolution of magnetic systems by ultrafast excitation. Essentially, atomistic spin dynamics is a multi-scale model, since for the parameterization of exchange, we can use first principle calculation in the form of a density functional theorem. We are able to access length scales of nanometers to micrometers, system sizes, and picoseconds to nanoseconds time scales. And we can use the output from atomistic spin dynamics into micromagnetic modeling. So far, until very recently, atomistic spin dynamics has considered a fixed lattice. However, by coupling to molecular dynamics, you can build what's called the spin lattice dynamics framework and also access the dynamics corresponding to lattice vibration and phonons. So both the atomistic spin dynamic and spin lattice dynamics framework is included in an open source code called Vampire. So this has been extensively developed in New York, with the lead developer being Dr. Richard Evans. And similarly, there's many resources online on YouTube and on GitHub. So now it's very easy for the community to perform atomistic spin dynamics simulation for various materials. And by employing high performance computing calculations, we can simulate large system sizes on multi-processor machines. So we can access faster simulation times and also larger length scales. So this was some of the theoretical framework behind atomistic modeling. So now I've chosen two applications. First is the 2D magnetic materials. So these were discovered in 2017. The two materials that were discovered were chromium triiodide and chromium germanium telluride. And these are very attractive since essentially you can access novel physics within the systems, and you can also build heterostructures where each of the layer has different functionality. So over the years, these have gained a lot of interest due to their potential application. So one materials that we investigated is chromium trichloride, which is a 2D magnetic system with an in-plane anisotropy, as shown in the schematics below. And we were interested to understand whether it's possible to control the spins in chromium trichloride via a laser pulse, via an ultrafast excitation. So for this, sorry. There's a animation here. I'm trying to, oh, here. So for this, we can shine a laser pulse on our 2D magnetic system. We observe at the beginning a lot of thermal fluctuation, a lot of thermal noise. And then what we observe is that our system relaxes and these areas are created, like the dark green and the orange areas are created. You can if you zoom in into this, these are vortex, anti-vortex structures. But interestingly, you also can observe annihilation of these structures and emissions of spin waves during this process. So by using a laser pulse, we are able to nucleate vortex, anti-vortex structures, merons, anti-meron structures, and observe a very rich dynamics into the systems. And by calculating the topological number, this Q, based on by triangulating our spin system and calculating this solid angle here, we are able to look at the how these annihilation and creation processes evolve over time. So this is one example of a topological chart as function of time, and we observe these step-like processes which correspond to creation or annihilation of merons, anti-meron structures, vortex, anti-vortex structures in our 2D magnetic system. Most of these 2D magnetic materials show what's called a type 2 demagnetization process. So this was introduced by Dr. Bert Koopmans et al., where essentially your demagnetization process happens in two steps. First, there is a quick demagnetization coming from the laser pulse, and then a slower decay of your magnetization coming from the elevated phonon temperature. And most of these 2D magnetic materials show this type 2 demagnetization. So this is one example of chromium triiodide, where we show an initial rapid demagnetization and then a slow demagnetization process. So we are able to reproduce this type 2 demagnetization with our atomistic simulation as shown here. However, when talking to our collaborators in Exeter who performed experiments on this type of systems, they observed some rich domain information which we were unable to see in this kind of initial simulations. So we were able to see a rich domain formation when we excited more strongly our magnetic system But by exciting so strong, the type 2 demagnetization process, the type 2 demagnetization form of your evolution of the magnetization curve was lost. So we are now back to a type 1 where we see this recovering. We observe the creation of domains, but we would like to also be able to our model to predict this type 2 demagnetization. So we went back to the 2-temperature model and created a generalized form of this 2-temperature model of this coupled equation between the electronic and phononic temperature. We assume that our 2D system is within a kind of a heterostructure form. So the 2D magnetic system lays within on a substrate. So under laser excitation, the substrate is also heated and can exchange energy and heat with our magnetic layer. We have looked at the generalized 2-temperature model for typical 2D magnetic system, chromium triodide, which chromium triodide behaves as a quasi-metal. So for very short time scale, hundreds of femtoseconds, the laser excites the free electrons into our kind of quasi-metallic chromium triodide, as shown by this schematics here. And we're able to model the spins with our atomistic spin dynamics. And then at longer time scales, chromium triodide has an insulated nature. However, the heated substrate can now exchange energy with the phonons in our magnetic layer, and the spins can further evolve given by that heated phonons dynamics. And with this generalized 2-temperature model, we are able to reproduce the 2-stage ultrafast demagnetization process observing chromium triodide. So we have the first stage, the quick demagnetization process, and then they have the second stage, which corresponds to the exchange of heat with the substrate and the elevated phononic temperature. And we are also able to look into the evolution of the domains during this process. So we're able to reproduce the type 2 dynamics and also the domain formation as observed experimentally. During the laser pulse excitation, there's also a loss of angular momentum, as shown in one of the initial experiments on nickel. So in 1996, this was shown, the ultrafast magnetization was shown on nickel and showed this abrupt change in magnetization and hence a very quick loss of angular momentum. And for a long time, the community was intrigued by where does this angular momentum go? And only recently, it has been shown that it can go at ultra-fast timescales to the phonons. So you can create these local strains into your systems, and then the dynamics of phonons will further evolve, and you can absorb what's called the Einstein-Dehaas effect. However, to be able to look at such experiments, we need to include phonons. So we need to further develop our atomistic models to include phonons. And we've done this in 2020. Until then, there were only a handful of people looking at such models, as shown in these references here. And the idea with spin lattice dynamics is that it can provide a very complete picture of a magnetic system. So we have three subsystems interacting in our magnetic material, the spins, lattice, and electrons. Electrons relax fast, so we can, in the first instance, consider them in equilibrium. So the full dynamics can be given only by modeling phonons and magnons into our system. And with this type of modeling, we're able to look into various effects, such as angular momentum transfer and Einstein-Dehaas effect, damping that comes from phonon interaction, and so on. The Hamiltonian has some modification corresponding to, in contrast to a normal or vanilla-like atomistic spin dynamic simulation. We include now the energy coming from the lattice, so we have a kinetic and potential energy, and our magnetic interactions are now position dependent, as shown here by the exchange. We also introduce a spin lattice coupling term, as shown here. which allows for change of angular momentum between a spin and lattice. We solve this coupled equation of motion as shown before. What's interesting is that we can basically neglect the damping term in the Landau-Lifshitz-Gilbert equation, so have just a precession term, since damping and dissipation will come intrinsically in our model from coupling to the phonon bath. Our model is able to pass relevant tests such as conservation of energy and angular momentum. And we also able to use various choices of potentials or of interatomic potential, Morse and harmonic potential. This is something more simplistic potentials, and we've implemented, however, it's possible to go to more kind of complicated forms of potential, such as embedded atom potential. So as I mentioned to you, we then test our model against, for example, reproducing the magnetization versus temperature curve in the absence of a spin thermostat. So only our phononic system is thermostated, and we observe that the magnetization is able to relax in the absence of an electronic thermostat only by coupling to the lattice. And we observe very good agreement between the atomistic spin dynamics, fixed lattice simulation, and the dynamics lattice simulation. So by neglecting the thermostat and introducing the thermalization via phonons, we are able to reproduce the same thermal properties of our magnetic system. We are also able to look at the dynamics properties, such as calculated the damping during our framework and estimating the damping during our framework. So we perform this magnetization relaxation experiments, and we can measure the damping as function of temperature and coupling of our spin lattice coupling term. The typical value we obtain of damping are corresponding with typical magnetic insulators such as IEEE, and the damping serves as a way to kind of parameterize our coupling term here. That allows us for angular momentum transfer between spin and lattice. And most importantly, we are able to look at the switching via phonon excitation. So going back to this switching mechanism that hopefully can provide more energy efficient switching. So we are able to excite our phonons via this periodic force. And during this excitation time, we observe that we have a strong response in the magnetization and even switching. But more importantly, we observed by calculating the spin temperature during this process, we observed that the increase in the spin temperature is very little, only in the millikelvin regime. Hence, we achieve what's called cold switching and non-dissipational switching. So we are able to reverse magnetization with very little energy dissipation. So investigated this for both harmonic and Morse potential for various frequencies, and you can find more details in the paper. And for details on the Vampire implementation, so the open source implementation, please check out poster A6 by Hamza, who has done a wonderful job adding all these features into our code. So in conclusion, we have shown that it's possible to understand complex magnetic materials such as 2D system via atomistic spin dynamics and understand how this couples to laser pulse excitations or various other stimuli. And we have also shown that by exciting lattice vibration or phonons at terahertz frequency, we can, this leads to more energy efficient storage technology and cold switching. And before I finish, I'd like to thank to everyone who has supported me and collaborated with me over the years, especially my PhD advisors, Professor Roshan Trail and Dr. Richard Evans, and also to the NEST group at the University of Manchester, who were very welcoming and helped me adapt to Manchester. Before I finish, I would also like to advertise a few opportunities. So first, I would like to tell you about the ChiroMag cost action, which allows early career researchers to access funding for short-term scientific missions. and travel between laboratories to perform research in the area of phonon switching. So we have this magnetized and chirality cost action that tackles spin lattice excitation for novel technological applications. So I recommend you to kind of check this out. There's also, we are planning a workshop, a vampire workshop that includes as well spin lattice dynamics simulations for the FAST conference in Thailand, which will happen in February. And also, I would also like to advertise Intermag. So Intermag is coming to UK next year at the University of Manchester. So I hope I'll see a lot of you guys there. I'm also open to PhD students. So if you're interested in this, please email me and I'm happy to discuss this further. So thank you so much for your attention. And looking forward for your questions.
Thank you very much, Mara. So any questions in the chat? Anyone wants to? Yeah, Moab, you can unmute yourself.
Thank you, Mara. Very nice talk. I just have one technical question regarding the part with the coupled spin lattice dynamics. Which numerical scheme you are using to solve the coupled system of equations? Is it something symplectic?
Yeah, so we're using, I'm not sure if you have it on the backup slides. We're using something that's called the Suzuki-Trotter decomposition. So we want our system to conserve energy and angular momentum. So we need to go through this more sophisticated numerical scheme, which essentially we do a update for the spin, velocity, position, velocity, and spin. And we have this is a second order Suzuki-Trotter decomposition. So we do another decomposition on the spin since they interact via the effective field. So indeed, for this type of spin lattice simulations, we need to look into more complicated integration schemes.
Yeah, and then do you arrive to do parallel computing with this scheme, or
Yeah.
it's not possible?
Yeah, it is possible to do parallel computing as shown here. So this is one schematics for a 2D system like. Okay, so you need to decompose your magnetic part into sectors. So when you do the parallel update, you need to make sure that the spins you're updating in those sectors are non-interacting. So for example, in this schematics here, you can update area 1, all the area 1 at the same time, since these are essentially non-interacting.
So it's somehow selective parallel computing.
Yeah, so sectoring, you need to do this extra sectoring.
Okay, thank you very much.
You're welcome. Thanks for your question.
Have a nice
Thank
day,
you.
Professor Maria.
Yeah, please go ahead, Howard.
Yes, I have some question about some last slides to present a few.
Yeah, sure.
Please no. Here you can perform some phonon calculation. Third harmonics.
Sorry.
Yes,
okay.
yes. I just ask you how can this decide this initial behavior like time very high simulation dumping process, but at time is go fast, the dumping is slow in the first figure. You can see. Please, can you explain something about this?
Sorry, can you repeat? Haven't been able to
Here,
fully
the
understand.
microscopic magnetization damping
Yeah.
is very high initially. I just ask a question, why the damping for initial step, like if I perform some simulation, if I perform some simulation by 10,000 number of steps, for initial number of steps, the magnetization is damping process. Why? Here you can in the initial 0 to 0.001, the damping is much, but as the time goes to higher, the damping is very slow. Why?
So in this particular case, the relaxation is so fast because you have a very high field on.
Okay.
In ultra-fast processes, what happens is that your damping and scattering varies dynamically, right? So with ultrafast demagnetization, at the beginning, there's a very high temperature. So your damping will be very high because you have a lot of modes available, Magnon modes, thermal modes available. And then you'll see some relaxation of that. So your kind of effective value of the damping decreases. So with this kind of particular slide, as you observe here, it's just a way to kind of quantify this damping, that effective damping. But this value of the damping is actually very low because it comes only from phonon excitation. So typically, yeah, when you observe this kind of very high damping with ultrafast processes, it comes from the fact that you have a lot of modes available, which then kind of relax.
Yes.